Well, happy Monday, Civil Engineering and Architecture class. Hoping you are taking the time to watch this video to get us started. There's quite a bit of calculating going on in this activity, so I don't really want to waste a Monday here, so making this a required assignment that you watch this video in its entirety, and then there will be instructions as far as how to begin and work through activity 2.2.3. So we are on the last activity of module, what are we? Module 5, I guess. Wow, I didn't even have it in there. It's activity 223, heat loss and gain. So if we slide down towards today, the 9th, Monday the 9th, you are going to watch this video that you're looking at right now with me, which is my take on the heat loss and gain PowerPoint. I would encourage you to take some notes as you work through this, and you'll use that information as well as the information on the instruction sheets on completing this activity. So here we go. We'll go ahead and jump right into the PowerPoint, and I'm going to link you into it right here. You can watch my video, and we'll get it in present mode. Here we go. All right, get these little X's out of here. All right, so we're talking heat loss and gain today. Kind of the next step, we've got our shed drawn, designed. Now we're going to use that as a tool to learn a few more things. We're talking about ultimately how big of a heater do we need? How big of an air conditioner do we need? So getting started here, the topics we'll be discussing here is heat transfer, heating system design, cooling system design. We'll talk a little bit about BTUs, a formula for calculating the heat load, the heat loss through a wall, how to determine that, the R value for walls, and then converting R values to the U factor. Those that had me for POE last year, I think this will make a little more sense, make last year's class make more sense. We'll put application to the thermodynamics. That's really what this lesson's all about, is applied thermodynamics. And we'll be using an engineering design data to determine what our our temperatures that we have to change. Uh, think about the temperature differential as we're calculating things, and then the total transmission load. So here we go. Let's just get right into it here. Heat transfer, what is it? It's the exchange of thermal energy between physical systems depending on the temperature and the pressure. And what that does is we're talking, it dissipates heat. So it always occurs from the region of high temperature to low temperature. I think we know that, okay? High to low, all right? We're trying to obtain thermal equilibrium so it equals out. So the temperature is the same everywhere, all right? So if it's hot outside, that hot is trying to get inside and equalize that. If it's warm inside and cool outside, it's trying to equalize that, trying to give you a loss of that temperature, the warmth going out into the cold, as is the case in winter. Some of the basic ways we transfer heat is through conduction, convection, and radiation, and we'll touch on each of those here. So if we create a comfortable environment, we want to have this to be efficient as we're designing our home, and we want to reduce the heat transfer between the interior and the exterior. And you can probably guess by now, we do that by airtight windows and doors and good insulation. So the first one we'll talk about is thermal conduction, the process for heat transfers through a solid by transmitting kinetic energy one molecule to the next. So if I have a piece of steel here and I've got something hot in this end, maybe a fire, or if I'm in the metal shop, a torch or a welder, it's going to create conduction, which means if I heat it here, that is conducting, and it gets warmer and warmer towards this end. Okay, what does that mean for our house? Okay, we have thermal convection is another one. Thermal convection is transfer of heat through the circulation of liquid or gas, gas being like air. So if you open up a window, we have convection happening, the movement of air. And again, like we talked before, it moves from hot to cool. And the third one is radiant heat. Radiant heat is energy that's transmitted as rays or waves, or in the form of particles. Think of the sun shining in. That's radiant. It's everything it touches is getting warmer. So what does this mean for a building? Which mode is represented by each of the arrows? When we think of each of these, well, we kind of have some leakage around a window. Which one do you suppose that is? We have leakage there. That's probably a case of convection. Convection being air movement. Okay. If we have air or heat transferring between a wall, we're looking at um, conduction, and then radiation would be the third one. All right, so if we've got sun shining through a window, and we're not talking leakage here, but sun shining through, that's our radiation. Conduction between the walls. Convection, as I mentioned, goes out the window here. What do you suppose is going on up in the roof or the attic of our home? Well, it could be a couple things. If we have an area that's not airtight, we could have some convection going on. We could even have some conduction going on. All right, so what does heat transfer look like? Heat loss occurs in the winter when we have a heating system that warms the inside air, and that inside air wants to get outside where it's cold. Remember, it transfers warm to cold, hot to cold. The outside temp is lower than the inside temp, therefore, it wants to transfer out. Heat gain occurs in summer when the air conditioning cools the inside air. So we don't want our house to get hot inside, but that's exactly what it's trying to happen. It's hot outside, that warm is trying to get inside. Outside temperature is higher, so it tries to transfer that heat inside of our house. All right, so we look at a couple little examples here. What do we have going on in the cold of winter? We have, it could be radiation, it could be convection, depending on how airtight something is. And we have summertime. What's happening there is that hot summer air is trying to get inside, again, equalizing hot to cool. So we want to look at the big picture of this and how this applies to CEA is in order to effectively heat a space, the heating system must provide at least as much thermal energy as is lost during the heat transfer. In other words, if our heater is not big enough, our house isn't going to stay very warm. So it's desirable to minimize heat loss, and we can minimize that conductance through the thermal envelope by creating better insulation, having our doors and our windows be airtight. Okay, we want to lower the U factor. We don't want that warm to transfer through those windows and doors. And of course, minimize convection, eliminate air leaks in the building envelope. So perhaps your family might do some things this time of year where you put plastic over windows. Sometimes we might put extra caulking around doors and windows. I just put caulking around some windows in my home that had a little bit of a gap between the frames. So again, trying to minimize the convection. So there's a number of things we can do to help manage or control that. We look at a cooling system. In order to effectively cool a space, that must remove at least as much thermal energy as is added through the heat transfer. So again, if we have a whole house, we're trying to cool it with a small, maybe a 5,000 BTU window air conditioner, probably not going to do the job. We make sure it's big enough to combat the amount of heat that it's trying to gain. So additional thermal loads for cooling might look at this. Solar radiant heat gains through windows. Occupant heat gain, figure about 250 BTUs per hour per occupant. Equipment heat gain, heat from things like computers and appliances, maybe your refrigerator or your freezer adds some heat. And then, of course, some lights offer heat gain. I think we've gotten better in that. A lot of our LED lights don't create near the heat as the old incandescent bulbs or even the fluorescent bulbs that created heat. So we're getting better with that. We start talking about our units of measure. The BTU is what we call that British thermal unit. It's what we use here in the United States, and it's defined as the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So 1 BTU is about the amount of energy by burning a match. Okay, that's BTU, a simple part of that. So if we look at Fahrenheit, that's our common temp that we use in the engineers and in heating and cooling and our what we call HVAC, heating, ventilation, and air conditioning, HVAC. BTU per hour is a way to measure the heating power of a system, such as a furnace, hot water heater, or maybe even your barbecue grill. So what does this mean for calculating our heaters and our air condition? This is an important part. You may want to write this down. You're going to need this in the activity. So if we're talking about heating, how many watts of heating we need? Well, 1 watt is approximately 3.4 BTUs per hour. So typically we figure about our figure heaters in BTUs per hour. So if we need to raise that 1 watt, raise it 3.4 BTU, we need 1 watt to accomplish that. If we're looking at the air conditioning side of things, 12,000 BTUs per hour is referred to as 1 ton in air conditioning applications. So a watt is what we consider for heating, and then BTUs, 12,000 BTUs in a ton for our air conditioning. We'll rate our air conditioners by the ton. We rate our heaters by the watts. All right, so what does this look like? The R value, perhaps you've heard of this. I think we've talked about with the insulation in the activity we just got done. We had R11 for 2x4 wall insulation. We had R19 for the 2x6 insulation. So what is that? It's the measurement of thermal resistance used to indicate the effectiveness of insulation. Okay, how much does it block the warmth or the cool from going through that? And the units there of an R value is feet squared times the hour times the Fahrenheit per BTU. The other side of that, and the inverse of that, if you will, a reciprocal, is the U factor. The U factor is the coefficient of heat conductivity. So how conductive is the material that you're using for insulation? It measures the flow or the transmittance through a material given a difference in temperature on either side. Now, if you had me for POE, a few of you have, that should start to ring a little bit of a bell when we did the heat box calculations, because we had to figure out the U value, and then from there we could figure out the R value. Okay. Units for that is in just the reciprocal of what we had here, it's BTUs divided by the square feet times the hour times the degrees Fahrenheit. So to calculate all of that, our Q is the total heating and cooling, is A is the area. Okay, so a wall, figure the area of a wall, for example. U would be the coefficient of heat conductivity, and we can find reference to these calculations to help us determine that. And then if we have this delta T, basically delta T is telling us big T in this case is the difference in temperature. We had a small t, we're talking difference in time. But so if we can figure out the total cooling or heating load, it's the area times the U factor times the change in temperature. So if we look at a wall, for example, there's no windows or walls in this, so we can just simply say, okay, it's 8 feet high, 12 feet long. We have an area, 8 by 12, 96 square feet. We then have to figure out our R value. Okay, so we can figure out the outside air film. We'll forget about that. But we have siding. Siding has an R value of 1.05. Insulation, there's the good stuff, 13 is the R value for our insulation. Our drywall, even though it's just sheetrock, that does have some R value to it, 0.68. And then we've got inside air film. We'll consider that as 0.68, giving us a total R value of 15.41. All we do is we add these numbers together. So a little maybe tedious in some cases because you have to figure out each of these layers of the wall. But once we've broken that down, as we have in our Revit drawing of our shed, it's easy to then figure out siding. I guess we did on this one, we don't even have the OSB layer that we'd figure each of the layers to figure out what's the R value. And once we have the R value, we can just from there calculate the U factor, which is what we'll use in our heat transfer formula. So what is the U factor? We just take the reciprocal of the R value. So the U is 1 divided by R. We had an R value of 1541. So 1 divided by that gives you a U factor of 0.06489. We can round that to just 3 decimal places. Okay, don't round up because we don't want to tell it, make it out to be better than it really is. All right, so if we're going to use that for a design, we need to do a little bit more work with that. So we'll choose our location. And for ours, I think the closest area we have to us is going to be rated as Rochester, Minnesota. So in your activity, you'll be calculating this for Rochester, Minnesota, which for weather statistics, that's close enough for where we're at. I don't think there's probably not much more than a degree difference, and we start looking at those types of things. We can gather some information from the International Plumbing Code. We can look at local weather data, and then NOAA, National Oceanic and Atmospheric Administration, gives us engineering weather data. So what does this all look like? Well, if we're going to be thinking about heating, we have to look at our design temperature. And if we're looking at our example here, and we're looking at Massachusetts, Worcester, Mass, our temperature, now we're saying our average temperature to heat up from is 4 degrees, okay? So what we're basically saying, if we want to heat our house up to 70 degrees, we have to heat from the average temperature in the winter of 4 up to 70. That means we have, 66 degrees is what we have to change our temperature. If it's summertime and we're trying to calculate cooling, we typically use the dry bulb, if you will. A wet bulb has to do a little more with the humidity, but we're going to focus on the dry bulb temperature. So again, if we're trying to figure out getting this down to 70 degrees, we would have to subtract 14 off from that. And we'll kind of show that as we move along here. So then our temperature differential, our delta T, is the difference between the design or the outside temperature and the design or inside temperature. Okay. Remember from the chart for Worcester, Mass, 4 degrees is our outside. Our design temperature, I guess 68 is what we use, means we need to change that temperature from out here to in here, 64 degrees. All right, so our total heat loss or transmission load works like this. Our area, which we calculated, is 8 by 12, 96 square feet. The U value, which we've calculated, it was R value, and then we just took the reciprocal. Change in temperature, because it's winter, we're trying to go from 4 up to 68, gives us a temperature change of 64 degrees. That creates our total heat loss load is our area times the U value times the change in temperature gives us 393.2 BTU hours. That's how many BTUs if all we had was that one wall. Now we need to figure all of our walls, doors, windows, so it all adds together. Okay, moving along here. I guess that kind of gives you the basics as far as how to calculate that. Now, let's take a look at our activity here. So you've got some basic ideas from that, I hope. And if we look at our activity, we've got links to this, and I'll jump back here. We've got links to this in the module. And what we are dealing with is, my video is kind of weird here. Our activity is right here. We have a spreadsheet you'll be working on, and that's where you'll put all your answers. But we also have a instruction sheet for this, and that's where we're going to start here. So you can get a start on this on Monday, then we'll spend some time in class on Tuesday, and maybe just a small portion of time in class on Wednesday, and let you finish that up on your own. So here's what we're going to do with this. So when the winter design temperature is below 60 degrees, the International Residential Code requires a dwelling to have heating facility capable of maintaining a minimum room temperature of 68 degrees, inhabitable rooms. Portable space heaters cannot be used to meet this requirement. A permanent heating system must be installed. And in buildings, we refer to heat flow in a number of different ways. The most common reference is the R value that we've talked about in the PowerPoint, or could be considered the resistance to heat flow. The higher the R value of the material, the more it will restrict heat flow. U factor, sometimes referred to as the U value, is a measure of the flow of heat thermal resistance. In other words, how much it can't flow through that. It's the resistance of that transmittal through a material given a difference in temperature on either side. So in the inch-pound system, the U factor is the number of the British thermal units, the BTUs. All right, I'm going to fast forward here. So what you're going to be doing is calculating this heat loss and gain for our shed structure. So calculations of the heat loss and gain are made to determine whether a proposal heating or cooling system is adequate to supply and to maintain desired temperature within a structure as specified by codes. Now, these calculations are also used to estimate the annual heating and cooling costs of a system. So I've highlighted a number of things on this activity here. Well, that we'll be using the 97.5% winter temperature, okay? And if you link into the codes, our building codes takes you to that. I have a link right to the page for the building codes, and we're going to Appendix D, as it says in the activity. Well, here's our 97% column. So you'll just have to scroll down and find Minnesota. Minnesota, where are we? Here we go. So from there, you can figure out your average winter temperature for Minnesota, for Rochester. That's where you'll find that information. We also need to look at let's see, some local. I think we have that from. You could actually look at one of those three, but this is the easiest. So you can get your data for Rochester right there. You're going to be using a calculator. You'll be using a little bit of your plan for the shed as well as some work from Revit. So you can use the shed drawing, but you'll use the wall and roof structures from your Revit file. If you think back to Revit, we put 2x6 walls in there, and I think we have I think we went a 2x8 ceiling in our shed, but we put 6 inches of insulation. Transmission loads worksheet, we'll show you that next. There's an R value chart, so I'll link to it right here. Gets you to a reference guide so you can start figuring what's the R value for all these materials. So linking into that, we can figure out our air film. We can look at our sheeting. I think we have OSB. Okay, we'll use medium density OSB. Things like our siding is on here, roofing is on here, insulation, but you can get all of your R values from that chart. Procedure is kind of spelled out, so take your time, read through this. In this activity, you'll calculate the total heat transmission load measured in BTUs per hour for the example utility shed, and you'll use the structure that we created and that we had drawn for our shed. So for this example, let's ignore the floor. As far as the doors go, I'm going to give you kind of a generic door to work with. So you can have one door, and it's a 72 by 7 foot door. As far as windows go, you're going to have just two single glazed windows. It's important you pay attention. That's single glazed, and each of those windows is 2 by 4. Okay, in other words, one wall has two windows, the other wall has none. So a couple different calculations there. Your desired temperature, in other words, your inside temperature is 70 degrees, and we'll be using Rochester for that. And from there, this will guide you through. If you follow through this, this gives you an example of how to calculate the R value. Again, it's just an example, so don't use those numbers. And each step, it kind of walks you through. Figure out your R value. So you're going to need to do this work in your engineering notebook and then put your final answer here. But as you work in through this, this is your guide, basically, that shows you how to do it. And there's questions there, but the actual work that you'll be doing is on a spreadsheet, much like this. And there are 3 pages to our spreadsheet. First one is your calculations. Okay, so that's your load calculations. So you're going to put your work in here, and the spreadsheet has formulas in it, which should make this kind of nice and easy for doing the calculations. So if we look down here, I think we're getting here. I thought we had a formula in there. Yeah, you may have to do some calculations. If you want to set up a formula, you can. It does not look like the formulas are in there. I thought we might have had it in, but you've had some experience with spreadsheets. You can calculate a formula there and use that. The second page is creating our R values. In other words, you need to list your R values here. You can calculate that, kind of do your legwork by using your engineering notebook and then just plug that information in here for your walls, for your roof, for your door, for your windows. Okay. That's where you'll calculate and determine your R values. And then you've got some questions at the end. We need to size out a heater and an air conditioner. Figure out pricing for one. Just use Menards to figure out the pricing for a heater. And then energy efficiency. And then you look at some changes. You'll do some changes here. Then you're going to go back to this page and you're going to make some energy efficiency changes and see what that does to our total transmission load. If we can reduce that number, that's really the goal of that activity. And then finally, some conclusion questions to go along. So I would encourage you to get a start on this on Monday. You've watched the PowerPoint. A great place to start would be right here. Why don't you go ahead and figure out your R values for your walls? Again, if your wall has a window in, you have to change your area. I think that's going to be more so back here. But what's your area? You have to figure out the area. The west wall, the east wall, north, south. On these north and south, one has a door in. Both have gable ends. So you have to figure out the gable ends. So you should work that out in your notebook as well. Show me some calculations on the calculations page. I think at the bottom here, there's some room for that. So that should give you an overview of where we're going and let you work with some numbers and see what we can learn about determining how big of a heater, how big of an air conditioner we need. All right, look forward to seeing you on Tuesday, but get a start. You've watched the PowerPoint. At a bare minimum, get your R values done today for your walls. And then if you want to figure out your area as well, but at bare minimum, I would say get your R values determined. All right, see you soon, guys. Take care.